Okay, so we're going to spend 2 days on this, which is factoring. And, you should have done some of this in Algebra 1, but if you didn't, then this will be your initiation to what we call factoring. And you notice it's not the first section, right? I'm starting with section 4.4 because this is the one part of the chapter which, we tend to struggle with, and it's really important to the rest of what we do in this class. So I want to get it up front so that we can quiz on it a couple times before we get to the test, just the way I'm doing it this time. A lot of this stuff won't make sense until we get to the end of the lesson. It'll make more sense not just at the end of today, but at the end of the next class, because we are going to spend 2 days doing all this stuff right here. So remember, quadratic. We talk about quadratic functions, expressions, equations. Quadratic, the word itself means squared. If you go to Latin or Italian or something like that, quadrato means squared. I speak Italian, right? So I know this word, quadrato, squared. Because otherwise you say, well, why do we call it that? Why do we just call it squared? Well, kind of in a way we are, but it's just not an English word. Okay, so remember, when it comes to math, right, there's 3 kinds of entities that we deal with. We deal with expressions. Expressions are something like x squared plus 5x plus 6, right? There's no equal sign. Up till now, what did we do with expressions? We simplified. Sometimes you can combine like terms. And we evaluate, meaning we plug a value in for the variable and we see what it equals, right? Equation is when you set that expression equal to something. If there's an equal sign in it, then we would like to learn how to solve that kind of equation. And a function is when it's actually equal to, the expression is equal to y now. So there's 2 variables, which means you're not going to be able to solve for x and get a value. What you can do is you can substitute or evaluate this expression for a whole bunch of x's. You'll get a whole bunch of y's, and then you'll graph it, right? Now, again, the thing that makes all of these things quadratics is this term right here. The fact that it has this x squared, right? That's why it's quadratic. And we'll see a little bit more on the next slide. But again, what we're going to do in this lesson, the one we're going to take 2 days on, is actually going to be working with the quadratic expressions, right? And we're going to learn this thing called factoring, which is going to help us to solve equations after that. Right? So let's go. You still writing? The next slide's the same slide anyway. But we add something that we do now to expressions, and it's called factoring. Okay, factoring. I put it in red because it's important. Okay. So the standard form of a quadratic expression is ax squared plus bx plus c, meaning there's no parentheses. The highest degree term, the highest power term is on the left, right? The next term would be the next lower power of x. There could be up to 3 terms in it, right? Because you could have a squared term, you could have a x to the first term, and you could have a constant term. That's the most terms you can get out of a quadratic, right? These are examples of quadratics. Right? They don't all have 3 terms, right? These 2 have 3 terms. But you call it, when it has 3 terms, those are called trinomials. Tri for 3. Right? And we use that word. It's not just a Jeopardy quiz question, right? These are quadratic trinomials. Okay, look at the next one. The x squared minus 4, right? It's missing a term, right? Which one of these three terms is it missing? The a, the b, or the c, right? It doesn't have the x to the first in it, so it's missing the b. The middle term's gone. What you call the linear term. That's the linear term because it's to the first power. And what about the last one? Which term is it missing? The a, b, or the c? The c. It doesn't have the constant, right? It's got the squared and it's got the first power, but doesn't have the last number. But they're all quadratics, right? As long as the a does not equal 0, it's a quadratic, right? The b and the c, they could be 0. That's okay, right? But you can't have the a be 0 because if you do, it's not a quadratic, right? Good. So there's 5 kinds of factoring that we learn about. And we're going to do 2 of them today. We'll do the other 3 on the next class. The first one, and this is, we have a new textbook, and same publisher, new book, and they've actually redone the way they teach it in the book too, which it's an improvement over what they did last year. I like it. So I'm just kind of going in their order, which is not the order we did last year, but that's fine. So we're going to do what's called a quadratic trinomial. What I call, this is not, the book won't say this, right? Nobody else probably uses this, but I call it simple quadratic trinomial because the leading coefficient, the a, is 1. It makes it a lot easier when that first number is 1, then the factoring is like a one-step process. It's very, very easy. And then we're going to do what's called greatest common factor, commonly abbreviated GCF. So, if you say, what kind of factoring is this? If you say GCF, we all know what you mean. GCF, greatest common factor. Right, these are the 3 that we'll do next time. And actually the one that's the hardest of all of these, by far, is this not simple quadratic trinomial. When a does not equal 1, then it's about a 6-step process to factor one of these things. Right? It's a 1-step process here. It's a 6-step process here. Right? The last 2 are just patterns. I say just patterns because they really should be kind of easy, but we tend to struggle with them. A difference of squares, difference means subtraction in math of 2 things that are being squared, right? And a perfect square trinomial would be something that could be written like a plus b, 2 things, 2 terms inside parentheses squared. Those are just special patterns, right? Most of the effort next class will be spent on that one right there. Good. Good, Justin. Okay, so what I call simple quadratic trinomial is when this number here, the leading coefficient, this a, is 1. So you don't even have an a. You just write a 1 in there. You still got the b and the c. And this would be an example, right? X squared plus 5x plus 6. That's simple because it's 1x squared. Now, this factoring, I have to tell you, your ability to factor depends on your knowledge of multiplication tables. Right? If you don't know the basic multiplication tables, I would even expand it and say the math facts, right? The things that supposedly you were taught in elementary school, but a lot of times weren't really taught to what we would say to mastery, but it kind of assumes that we know these things. Like the kind of thinking you do when you factor something like this is you look at the last number, the thing that is C, right? And you say, what two numbers, what are the factors, meaning what two numbers multiply to give you 6, but they add to give you 5? So you got to be able to think, what are the factors of 6? 1 times 6, 1 times 6, or 3 times 2. Okay, which one of those adds to 5? The 3 plus 2 is 5, right? So you have to know your multiplication tables because that's always where it starts. Find the factors of the last number and see which pair of those numbers add up to the middle term. That's the thinking, over and over and over and over again. Now, if you are not strong with those, and believe me, I'm not trying to, be overly critical here. This is what we see all the time with all the students, that you were not really taught those math facts really deeply. So what I have here are some multiplication tables. They might help you as we're going through stuff if you want to see, what, like for example, for 6, there's the 6. Okay, that's 2 times 3. Okay, you probably didn't need it for 6. Okay, what about 56? What are the factors of 56? 8 times 7. I mean, that's the main one you think of. It could be 4 times 14. This is just up to 12 times 12, but you'd be able to find most of the things you need right there. It also has at the bottom of that a list of all the perfect squares. When we do this difference of squares thing, it depends on us recognizing when we have a square, a perfect square. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Those are perfect squares. And if you don't recognize them, you're looking at it going, I don't know what I'm supposed to do. If you recognize them as perfect squares, then, it suggests the method to solve it right there. So I'll probably, as from now for a long time, this book of multiplication tables, which has the Algebra 2 formula sheet on the back side, will probably be sitting over there next to the calculators. If you want to take one, you can take one. Okay. So let's see how this works. Examples, right? Again, the thinking that I'm going to do, these are two separate problems. Okay, I have to think of the factors of 42. Is that right? Yeah, the factors of 42 that add up to 13. Okay, so can we think of factors of 42? I mean, it could be 1 times 42. It could be 2 times 21. Who said it? 6. It could be 6 times 7, right? It could be 3 times 14, and it could be 6 times 7. So any of these that you add up, do you get 13? The 6 and the 7, right? So once you find the factors that add up to that middle number, right, those are the two that you want. And so the factoring works like this. You're going to write 2 sets of parentheses, and inside both sets of parentheses, they'll start with an X. Right? And then we said 6 and 7, so it'll be plus 6 plus 7. Plus 6 plus 7. Now, if you want to know why, what did we do right there? Okay, first of all, what did we have here? We had 3 terms, right? We had x squared plus 13x plus 42. That's 3 separate terms. When we factor, we turn those 3 terms into 2 factors, 2 things that are being multiplied together now, right? That's x plus 6 times x plus 7. That's what we mean by factoring. We're turning these into things that are being multiplied together, factoring. And that's going to help us to solve equations when we get done with this section after a couple of days. Then we learn how to solve quadratic equations. And one of the main ways is by factoring. Okay, and I'll leave that for later, but I'll just say that that's why we're doing this. It's going to help us to solve equations later. Now, you can verify that this came from that by multiplying these two together. Do you remember the process to multiply Two things times two things. Everybody remember FOIL? FOIL, F-O-I-L, right? If you want to multiply these together, you remember what the letters stand for? First, outer, inner, last, right? So multiply the first terms in each set of parentheses. X times x is x squared, right? That's the first. Okay, then multiply the outer terms, meaning the x multiplies with the 7. That's plus 7x. Right? And then we multiply the inner terms. That would be, so that was that. That would be the x times 6, or 6 times x. That's 6x. And then you would do the last terms in parentheses, which would be 6 times 7. And that is 42. Right? And then you have two like terms, 7x plus 6x, which is 13x. Add the coefficients, right? X squared plus 13x plus 42. I mean, you could see when you FOIL these where that thinking comes from. You know, that find the two numbers whose product is this and whose sum is that. I mean, there's the sum, and 42 was the product, 6 times 7. That's how all that came together. But try the next one. What are the factors of 24 that add up to 11? Say again? 8 times 3. Now, 24's got a lot of factors, right? 24 could have been 1 times 24, 2 times 12, 3 times 8, 4 times 6. And the two that add up to 11 are these two right here. Okay, so what goes inside each set of parentheses? Bree? Okay, the first thing is x. And what comes after? Plus 3 plus 8. Okay, you don't have to FOIL it. Okay, to me, I FOILed this just to show you where this came from, where that thinking of finding two numbers whose product is that and sum is that. I mean, if it helps you to see that a few times, right? X times x is x squared. X times 8 is 8x. X times 3 is 3x. And then you get 3 times 8. I'm going to write it like that. So you could see the middle term will be the 8x plus 3x. The last term will be the 3 times 8. That's why we're looking for the factors of 24 that add up to 11. Right? That's why it works. Do you remember doing this before? I mean, this is the first time you've been in Algebra 2, is this the first time you've seen this, or did you do it in Algebra 1 a little bit? Okay. So try this one. See if you could figure out how to factor that one. Does anybody want one of these multiplication tables to help you through it? Anybody? Anybody? Sam, come on, Sam. We need your participation. Does anybody want a multiplication table? Anybody? Do you want one? Okay. So, okay. Do you want it? Okay. Who's got an answer? What does it say? X plus 5 times 6 plus I see one right answer. Get it? Yes. Did you get it? Yes. Hunter. Yes. Justo. Okay. So what were the two numbers? 7 and 5, right? So once you've identified, 35 is 5 times 7, right? And those add up to 12, then it's a one-step process. X plus 5 times X plus 7. Done. And you don't have to do the FOIL part. I saw most of you were doing the FOIL part. You don't. If it just says factor, then that's not necessary. Okay, now these examples, right? Our numbers are always positive, right? That's why when you multiplied them, you got a positive number, and when you added them, you got a positive number. Okay, that's not always the case. Right? Notice now that when we multiply these numbers, we're getting a positive number. But when we're adding them, we're getting a negative number. What does that tell you about the signs of those two numbers? They both have to be negative, right? To get a positive through multiplication, it's either a plus times a plus or a minus times a minus. And if they're adding up to a negative number, it must be a minus times a minus, right? So let's see. What are the factors of 30 that add up to 11? 5 and 6, right? 5 and 6. I mean, 30 has a lot of factors, right? 1 times 30. I mean, if you notice, there's a lot of these factors that you could generate just like I'm going to do right now. Like I'm going to double the 1 becomes a 2 and the 30 becomes a 15. Just cut it in half, right? Or let's see, 3. Does 3 go into 30? Yeah. So that's like 3 times that, so that's 3 times 10. And then we've got 5 times 6. And the ones that add up to 11 are these. But because it's negative, they must both be negative. Right? So how does it factor? X. I wouldn't say plus negative, just say minus. X minus 5. X minus 6. Okay. When the last number is positive and the middle number is negative, they're both negative. Right. What about this one? The factors of 54 that add up to negative 15. We'll just think the factors of 54. Right. Look in your if you've got a multiplication table, where do you find the 54? 54, 54. 54 is, 9 times 6. So you can find the rest, but we're going to end up with 9 times 6. But because this is negative, it actually is going to be negative 9 and negative 6. So what is the factoring of it? X minus 9 times X minus 6. Done. Right? So if you know the multiplication table, it's a really easy process at this point. And again, this is called factoring because we're turning these three terms into the multiplication of two factors. And it's going to help us when we get to the next step where we try to solve equations, right? We can't solve that. We can solve that, right? That's why we learn this. Okay. We good? So try that one. Same pattern, right? Last number's positive, middle number's negative. Yeah. Mm-hmm. for a lot of numbers, I mean, they can have a lot of factors, but there's like maybe one set of factors that kind of come to mind all the time. For me, for 40, I would think 5 times 8. But does 5 do, is 8 plus 5 14? No. So something's wrong. That's right. That's right. That's right. You get it, Hunter? Okay. So what are the two numbers? -4, -10. Right, so it's going to be x minus 4 times x minus 10. Okay, does it matter if you happen to have written x minus 10 times x minus 4? Which property is it says that when you multiply things, the order is not important? Somebody? Commutative, right? 2 times 3 equals 3 times 2. It doesn't matter. I mean, don't think if you wrote it differently, you did something wrong. It's the same thing. Okay. Okay, now we move on to the next possibility, which is that actually the last number is negative. Well, what does that tell you about the two numbers that when you multiply them, you get a negative? One has to be a positive, one has to be negative, okay? But if you add them up and get a negative, which is the bigger, the negative or the positive? If you add them up and the result is negative, then the bigger one is negative. I mean, so let's see, for 48, I'm going to think 48 could be 1 times 48. It could be 2 times 24. It could be 3 times 16. It could be 4 times 12. And it could be 6 times 8. And then I know that the bigger one of those has to be the negative, because when I add them up, I get a negative number. So let me put minuses in front of all of these, right? And which one of those gives us -2? 6 and -8, right? Right there. 6 and -8 give you that. So that this will be x plus 6, x minus 8. Okay, let's do the next one. 15, it's a -15, so that means one factor is positive, one factor is negative. They add up to -14, so the bigger number is going to be negative. Let's see, 15 has only got two possibilities. It's either 1 times 15 or it's 3 times 5. And the bigger one would have to be negative. Which one of those adds up to -14? This one, right? So this is x plus 1 times x minus 15. Okay. So try this one for yourself then. Factors of 60. I mean, think of so now obviously everything could be always, yeah. What do you say? If you can always say 1 times itself, right? 1 times 60. Obviously, 60 is an even number. You could double that, make it 2 times 30. Is 60 divisible by 3? It is. Do you know how you could tell if a number is divisible by 3? Add up the digits. 6 plus 0 is 6. Is 6 divisible by 3? Yes, so it's 60. So that would be 3 times 20. 4, yeah, it's actually divisible by 4. Oops. And how about 5? 5 times 12. And 6 times 10. That's a lot of them. And the bigger number is negative because it adds up to a negative number. So which one of these is our 2 factors? 5 and negative 12. Right, so x plus 5, x minus 12. Good. Which leaves one more possibility, right? What if the product is negative, which means one's positive and one's negative, but the middle term is positive? What does that tell you about which number is bigger, the positive or the negative? The positive's got to be the bigger, right? Because when you add them up, you get a positive number. So 72, right? If I think of factors of 72, that would be 1 times 72, 2 times 36, 3 times 24, 4 times 18, 6 times 12, and 8 times 9. Now, because this is positive, you know that the bigger number is positive. It's the smaller number that's negative. So which one of those adds up to 6? The negative 6 plus 12, right? That's the one that gives us that. So the factoring would look like x minus 6 times x plus 12. About 45. Can anybody think of the factors of 45 real quick? There's not too many of them. Negative 5, positive 9, right? Negative 5 times positive 9, right? When you add them up, you get 4. So x minus 5 times x plus 9. So try that one. Last number's negative, middle number's positive. You got it? Yes. Get it? Yes. You got it? You got it? Here? No. Here. Correct. Correct. So people are mostly getting it. What are the two numbers? Positive 10, negative 5. You're good. Positive 10, negative 5, right? That'll give, when you multiply those, you get negative 50. When you add them, you get positive 5. X minus 5 times x plus 10. Done. Right? This is factored form. That's standard form. Right? They're the same thing. Okay. I think the next is, am I in the right slides here? Yeah. Okay, the greatest common factor factoring. We struggle with this more than we should. And the thing is, it's really important. I mean, every time you factor, when you're presented with an expression, this is the first thing you should think about. Right? A lot of times there's going to be like more than one kind of factoring in the same problem. Usually it's that you had to do some what we call greatest common factor factoring, and then there might be, for example, the simple quadratic trinomial after that point. So you always want to check for this one. It will make problems much easier. Okay. And actually, this kind of factoring is not just for quadratics, meaning where the highest power is 2. We will use this in chapter 6 when we go up to the higher powers, polynomials. And it's kind of like this kind of factoring. You could think of it like a reverse distributive property, right? In the distributive property, you know, you have a number outside parentheses and then more than one term inside, and you distribute the 2, you multiply both things inside the parentheses by the 2, right? So you get 2x plus 6, okay? In greatest common factor factoring, it's actually the reverse. You try to imagine if there is a number that I could take outside parentheses to make it look like that. And really what you're trying to say to yourself is, what is the greatest factor that the terms that you see have in common? Like you could look at 4 and 8 and think, okay, well, they're both divisible by 2. That's true. But is 2 the greatest factor they have in common? No, 4 is the greatest common factor, right? So you take the 4 outside the parentheses. Now what happens if you divide 4x by 4? You just get x, right? Or if you divide 8 by 4, you get 2, right? So you got to figure out what's left behind when I take out the 4 in front of the parentheses. And it's a divide, right? If you take 4x from 4 from 4x, what's left? Just the x. But it's really a 4x divided by 4. It's an 8 divided by 4. Right? And what should be the case, and you really need to check this, is that you should like go in reverse and see that you don't get back to where you started from, right? See that 4x distributive property, 4 times x, 4 times negative 2, you get back to where you started from. Then you know you factored it correctly. Right? There are some common places where we make mistakes with this that you don't get back to where you started from. So here's a couple examples of this. We're almost done. Look at this expression here. What would you say is the greatest common factor between the 7n squared term and the 21? 7. Looks like 7, right? So that means you're going to take a 7 outside parentheses. And then what does it do to the first term if you take away the 7? It just n squared. Right? If you take 7n squared divided by 7, it's just n squared. Right? What happens when you take 7 from the 21 term? It's like 21 divided by 7 is 3. Okay? So just to verify, you know, make sure that if you go in reverse, do the distributive property, that you don't get this back again. 7 times n squared, 7n squared. 7 times negative 3, negative 21. That's the factoring of it. Okay. Now, what's in common in the next term? The greatest common factor between 4, 8, and 12. Are there any x's in common? I mean, there's x's in this term. There's 2 x times x, and there's 1 there, but there's none there. So there's nothing in common to all 3 terms. But there is a 4, right? So I'm going to go like this. 4 times x squared plus 2x plus 3. Right? And notice, I hate it when it does that. Notice, right? You know, I just divided. 4 divided by 4 is 1x squared. 8 divided by 4 is 2x. 12 divided by 4 is 3. And if I do distributive property, 4x squared, 4 times 2, 8x, 4 times 3, 12. So it works. Now, the question you got to ask yourself when you get to that point right there is, could I do any more factoring? I mean, that looks like our simple quadratic trinomial. It has a 1 in front of the x squared. So can you think of factors of 3 that add up to 2? I mean, what are the only factors of 3? 1 times 3, and what do they add up to? 4. So it's not factorable, so you're done, right? But you need to check. You know, when you're left with something inside parentheses, you check to see whether it's factorable again. And this one is not, so not factorable. Okay. Okay. So try to factor that one. Is there a greatest common factor? Let's do it. Is that factorable? There's an x there. Right? When you take a 9 away from there, there's still an x. So is that factorable? What's the greatest common factor? There was a 9. You know, I'm seeing just about everybody's got the 9, right? So you take out a 9, and what's left in parentheses is x squared plus x minus 2. So again, you got to ask yourself the question, is that factorable? What's inside the parentheses? Can you think of factors of -2 that add up to +1? And the hint, yes, you can. What would they be? Say again? What are the factors of -2 that add up to +1? I mean, what are the only factors of 2? 1 times 2, right? And one of them is negative and one of them is positive. Which one is the positive has to be the bigger of the 2, right? So you look, if this is -1 times +2, does that add up to 1? Yeah, -1 plus 2, that's it. So this is, you can actually take this one step farther. You can say 9 times x minus 1 times x plus 2. Right. So whenever, usually you start with greatest common factor, you might have something else to do when you get done with that. You need to check. Yeah. What's that? Oh, no. From here to here? No, we never did. Whenever we factored our trinomial, we ended up with x, only x, not x squared. Okay. There's one more example I want to show you, just because the book didn't have any examples. Even the homework problems don't have any that show this one thing, and it's where we always make the mistake when we do greatest common factor. Right? What would you think is the greatest common factor between those two? There's a 2 in common. What else is in common? I mean, when you see x squared, that's like x times x. That's twice, right? And this has got an x in it. So they each have a 1x, right? At least they have 1 in common. So you would say that 2x is the greatest common factor. Right, now, what's left when you factor a 2x from 4x squared? What's left? 2x, right? Remember, you want to be able to multiply 2x times 2x and get that, and that's correct. Right? Now, what's left when you take the 2x away from 2x? Not 0. 1. Okay, don't, just if it looks like you're doing that, remember what you're really doing is you're dividing, since we took a 2x out in front of the parentheses, we're really dividing each of these by 2x. And 2x over 2x is 1, right? If you didn't have a 1 there, then when you did distributive property here, you wouldn't get the 2 terms back. You need to have a 1 there so that this is equal to what you started with. So every once in a while that happens, right? You're factoring the one number, that factor is the whole term. It looks like the whole term. Make sure you leave a 1 behind. Okay. It took longer than I thought. We're good? So that was it. That's the first day of it. We'll do the rest on next time. These problems, I think these are the greatest common factor. All these are the simple quadratics. You know, if you can just think of those 2 numbers, it'll go really quickly.